All right, I got a lot of gadgets going. Hopefully it doesn't crash. We're going to find out. I finally figured out how to, I'm recording these lectures for you, right? And you got the YouTube link and other things. And I had an interesting conversation with a professor in biology who said, why do you do that? Because that's really not good for students. Do you guys like them? Okay. So you can go, sometimes you can go back, and people are fast. So again, I think don't use it as, a way to not listen during lecture and things like that, or not pay attention during lecture, but maybe it can help you to reinforce things and help you understand some material maybe that you don't understand. So that's kind of how I would use those recorded lectures, but they aren't a panacea for everything. But anyway, okay. So I'm now trying. So a lot of times what I find is I get stuck on PowerPoints, and I don't write text and I don't slow down. So now I'm mirroring my iPad to my MacBook Pro desktop through QuickTime, and I figured out it's much more stable than the way I used to do it. So hopefully that'll work. We'll find out. If it crashes, who cares, right? Okay. Okay. So and then the other thing is, again, no labs this week. Labs start next week. I should have the PDFs for I think the first 5 labs up on Moodle. Each one will be put into their respective week. There should be a sort of the text, the narrative, and then the answer sheets and tables. So, so hopefully I'll have those up today. The other thing, oh yeah, the iClickers. I'm now running those. I got up to speed. I'm now running those all through Moodle. So they go right into the gradebook. So you have to register your iClicker on Moodle, I believe, in my particular course, right? So, yeah. Yep.
I think if you register like before, it's fine, because I tried to register, but my iClicker's already registered. So.
In Moodle?
Yes.
Okay. So it probably finds your UNO email and populates it in each course.
I think that's
okay. I'll find out. So anyway, we're going to do a little iClicker thing today. It's not going to count towards attendance or anything like that, but just to make sure kind of you get used to how we do things. Okay. So yeah, if you've already registered, so when you went in to try to do it, it said you're already registered. And okay.
You have that number on the back of your iClicker, and I think it runs with your student ID number.
Okay, good. So that'll be much more stable, and it's not on my desktop, and it'll be recorded in your gradebook too, so you'll be able to see it. Okay. What I want to do, at least today, is this is an area of biology that's extremely interesting to me. Before I became a brain dead administrator, I used to be a researcher, right? And I still have graduate students, but I'm not. So one of the things I'm really interested in is reproduction. And one of the things I'm really interested in is whether organisms should reproduce sexually, that males and females mate, versus asexually. And I studied organisms that can do both. Another key feature of sort of evolutionary reproduction is what's called sex ratios, okay? And this is usually a phenomenon that you look at within a population. And you characterize what's the sex ratio of males and females in a population. And this was a phenomenon that everybody looked at. R.A. Fisher in the 1930s, a very famous evolutionary scientist in Britain, developed a model to explain this phenomenon. And the phenomenon's real simple. Most organisms, what kind of sex ratios do you think you find in most organisms in terms of the percentage of males and females within populations? Yep, it's mostly 50-50, okay? And that's a phenomenon in nature. Not all of organisms have it, but it's a very common feature. So Fisher was interested in explaining that. Part of the problem is it doesn't make a whole lot of sense in general, because when you think about it, and I know certain members of this audience will become uncomfortable about this, but Fisher argued that basically males in many organisms don't serve much function. And that is, males aren't reproductive. Okay, and oftentimes certain kinds of organisms, they don't provide much paternal care and all those sorts of things, and the argument has always been females produce offspring, males just provide sperm and not much beyond that. So why not produce mostly females in a population is kind of the basic argument, okay? And we'll be spending, as we get into the second part of the course, there'll be a whole lecture on that. So I'm just kind of, so these were the sort of things that Fisher was trying to, and he developed a model. It's outlined in your book. Do not get bogged down in the derivation of that mathematical model. It's not that complicated, but I'm not interested in that. What I'm interested in is understanding how we test this hypothesis, what kind of data, and how this really demonstrates natural selection that occurred in about 10 generations or 5 years. And so I'm going to go through it. Okay, so this is the butterfly in Samoa, and it's infected by, I think it's a protozoan parasite. It's an intracellular parasite that actually does some unusual things, and you could spend a whole semester like I did in graduate school looking at these dynamics. This is a thing that kills, this is an intracellular parasite in a lot of insects, and especially butterflies, that kills males. It kills male embryos. So it's a thing called Wolbachia, and it kills male embryos. And we're not going to go into why it might do that, but it does, okay? So what happened in this particular population is they got infected by Wolbachia. Guess what happened to the sex ratio? It was originally 50-50. Guess what happened to it very quickly? It went to 99% female and about 1% male. So that was the observation made. That was the initial starting point in this population. And so the sex ratio theory suggests something else, right? This is not really a stable ratio. And so when we think about sex ratios, we often say they're evolutionarily stable and they go back to what we call an equilibrium. So we're going to be talking a lot about equilibria when we get to population genetics and looking at gene frequencies changing over time and going to an equilibrium and all these sorts of things. So you're going to be looking at what are called equilibria. But this sex ratio, where it goes to 1-to-1, is an equilibrium that all populations should go to. So, okay. So if you had 99% females in a population due to this Wolbachia, what would the expectation be? What would you predict would happen over time?
Males would mate several females, or that she would start reproducing on her own.
Okay. So that might be the other thing. It might lead to, we're not going to go down that path. It might lead to asexual reproduction. Okay, that's a good idea. What's another thing? So when you think about this as an interaction. It's between a host and a parasite. Butterfly's the host, right? The Wolbachia is the parasite. So we can think about the response is going to be at these two different partners in this interaction, and we'll look at that. But let me just tell you what happened. So why does that turn off? Okay. It says it has a, oh, I don't know. Where's the, somebody showed me this yesterday. It's supposed to have a, okay. Well, I'll figure out where the pointer is. So what happened? So they were originally about 99% female, and this was about 5 years later after the introduction of Wolbachia. What happened on this island? It basically, in most of these cases, it overshot it a little bit, but it went back to about a 50-50 sex ratio. So the males increased in frequency. Okay? I don't know, and your book doesn't discuss what happened there, but we can make a hypothesis. So the question is, what happened here? So when you think about this, what Fisher developed was a very simple theory, and his idea was very straightforward. He said a real simple thing, and the calculations are in your book. So the idea here is real simple, that in a population where a sex is rarer, right, that's below 50%, the simple idea is it has a reproductive advantage, okay? So those males, right, had access to a lot of females, and they probably had a higher reproductive success. And there's a formula in there, and you can look at it. But let's imagine in some case that there were, in a population, there were 10 males, and in a females there were 90. Okay? So that's 10% males, 90% females. Imagine out of those females, out of this population, 100 offspring were going to be produced. Fisher's model has a pretty simple equation to actually figure out what's the expected reproductive success of those two sexes under that scenario. And it's real simple. And you're not going to have to calculate. I'm not going to ask a multiple choice exam. There's not going to be an essay question on this, but it's a real simple equation. The male reproductive success is, the numerator is always 100 divided by 10. The female reproductive success is obviously 100 over 90. That's equal to what? 10. That's equal to 1.1. Okay? So the basic idea here is males have this huge, they just got access to all these females. A mother that overproduces sons in that population is going to have a huge reproductive success. And they go on in the book about grandchildren. Don't worry about that. The basic idea is they have much higher, the rarer sex has a much higher reproductive success. What happens, do you think, if the males went to 90% and the females went to 10? Where would it go? It'd go back the opposite direction. The idea is it always goes to that, what's called an evolutionarily stable ratio of 1 to 1. Okay? So that's the basic take-home message. This is the prediction from Fisher's theory, that if you ever have a deviation and one sex is rarer, that sex will have an advantage and it'll push the sex ratio back to that equilibrium. So that's the basic take-home message. So what do you think happened, though? So did this population evolve? Did it change? Okay, it changed. The sex ratio changed. But the question we might ask ourselves, what changed? So let's look at it from the perspective of the parasite, right? So Wolbachia, is the parasite, and here's the host, the butterfly. So you saw males increasing. What do you think might be what do you think might happen from the time Wolbachia was introduced to 5 years later? What might happen to Wolbachia that would result in more males being produced? What would be a potential response? Come on, yeah. And let me tell you what I would normally do. What I would normally do, I'd present this hypothesis, and then I'd ask you to work in 4 groups and tell me the answer. I might give you some bonus points if you came up. Okay? Any thoughts on? Mm-hmm. Mm-hmm. But the males still are being produced, right? So what might be happening to Wolbachia in terms of its effect on the host, do you think, from that initial time to 5 years later? What could be a response? Yeah, kind of immune, but maybe they became less deadly, right? Maybe their effects on male embryos got reduced, right? There was selection against that kind of response. So that's one possibility, at least from the parasite's perspective. Its ability to kill males was under selection for reduced action on males is one idea, okay? So it became less deadly. Okay, that's one option. What do you think might be the option from the host, at least? Here, it's infected with an intracellular parasite that kills its males. What do you think selection is acting on in that butterfly host? Yeah, so the idea here would be some mechanism by which they can resist that parasite and kill that Wolbachia, right? And thus limit its ability to kill the host, kill its embryos. So maybe resistance. Okay. Yeah, that's another. It could be, and that's a possibility. I'll tell you what the answer is. It's not that, but that's another good way. So this is what I think is the fun part, just thinking about things, coming up with hypotheses, and how do you then test those, right? Okay. So how would you test that top one? That's a harder one. So if you're saying that Wolbachia in that population it basically has lost the ability to kill males, how would you test that? Yeah, what they did is they isolated the parasite from the butterflies, right, from those populations after 5 years, and then they infected something. What do you think they infected? Not those butterflies. What do you think they infected? Yeah, some other butterfly from some other island that never had interaction with that parasite is what they did. So they did it in the lab. They isolated the Wolbachia. They brought in butterflies of the same species from somewhere else, not too far away. They infected them. Guess what happened to those butterflies that got infected? Guess what happened to their sex ratio? All the males died. Okay? So from that, what would you reject that hypothesis? That Wolbachia became less deadly? Yeah. So the basic take-home message, uh-oh, it froze already. Okay. Oh, I'm on the wrong one. Jeez. Don't get old is all I got to say. Okay. So that was rejected from that piece of data. Okay. The other thing I'm not going to go into, what was supported was the butterfly resistance. And it turned out that these butterflies had a genetic mutation that created some sort of antigenic a response to these parasites that killed the Wolbachia. Didn't kill them. They had really higher levels of resistance to the parasite. Okay? So this hypothesis was supported. The key take-home message here is pretty simple. The evolutionarily stable sex ratio hypothesis was supported. It went back to 1 to 1, and the mechanism was that the butterfly developed resistance and reduced the effect of the male-killing Wolbachia on it, not the other way around. Okay? And there's a lot more detail in the textbook. So any questions? Does that make sense? Okay. Let me you want to do an eye clicker? Sure, let's try it. Okay. Make it real simple. What I'm going to usually try to do, and I change, usually at the beginning of the class, I'll put up a multiple choice question like from the previous lecture period, right? And see what you remembered or, those sorts of things. And some of these eye clicker questions may even show up on the exam. You never know. Okay? So what I'll try to do is I'll try to do that every time, and then the middle will do probably an eye clicker question, then often thought, where you break out in groups of 3 to 4 to write answers to questions and more kind of thought questions rather than multiple choice. So, okay. So let's do, is everything on? Okay. And again, this isn't going to count if you don't have it. Don't worry about it. I just want to make sure the system is working okay. So you probably want a question, right? Okay, here's the question. Yeah, oh, hey. Oh, I don't know. Does it matter? AA probably. Yeah. Do you have to? Oh, okay. Yeah. The little box. Eye clicker system. I think it's AA. Yeah, I didn't change it. I kept it. That's the default. Hopefully there aren't other. So I guess the issue is if there are other people. Okay. 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 So the evolution. I hope this is an easy one. So The evolution of antibiotic resistance is a result of A, artificial selection, natural selection, genetic inheritance of acquired characteristics. Again, let's go ahead and let me see if I can start this from the remote. Oh, I should turn it on. Oh, the base frequency code is AA. Okay, here you go. I only give 15 seconds to answer, then shut it off. No, I'll give you 30 seconds to it. Some of the other questions are a little more tricky. Okay. Is everybody in? Stop? It doesn't really matter. Okay. Oh, maybe it was a little harder. Huh. Okay. I'm not going to confront you. Okay. So, what do you think? The inheritance of what does it say? Inheritance of what? Acquired resistance. Okay. That's kind of like acquired inheritance, which we really didn't talk about it, and it kind of deals with sort of non-genetic mechanisms of adaptation and that sort of thing. So that's kind of wrong. Well, it's definitely wrong. So the answer is what, do you think? Natural selection. Okay, so that's kind of the simplest. And I think the inheritance of acquired resistance was a little vague. We hadn't really talked much about it, and so anyway, so this is the process of natural selection. Okay. So again, it's not artificial. Why is it not artificial selection? This is an important thing to think about. Yeah, because humans aren't making the choice of what are the particular kinds of traits that are propagated and favored and those sorts of things. It's a process that's determined, of course, outside of human in some sense. Humans are setting the stage for antibiotic resistance, but we're not selecting that for desirable traits. Okay. Okay, good. So we got that working, I think. I'm going to stop the recording here so they don't get too long.